Good afternoon, everyone. And I'm going to have to go really fast since Zach took up so much time. I'm going to give a presentation about engineering and an overall view of everything and some depth on certain projects. Also, when I've gone through the slides, and Jonathan will be part of that, we have several of our engineering team here today. And I've asked them to come up and give a little 5-minute elevator speech, if you will, about what their system is or what they're working on. With could be anything from golf to Fox Plus to an Ascent. Which buttons go ahead? This. I'm not really good with this fancy stuff here. I'm going to skip that because that was actually a leftover from the board of directors. But it's pretty much actually what is in here. A little bit about the team, and then the programs mostly, and a little touch on future projects. So looking at the team, and this is an interesting statistic. We have about 35, 40 members perhaps of the team, and we had asked them to all give us their date that they started with AMSAT engineering. So I ran that through and put it into a chart here just for curiosity, and it comes up with a kind of an interesting look at who we have with us now. We have a couple different groups, the group of the first three there, and Bill Reed is the farthest left there. What year did you start in here, Bill? 1981? Well, I didn't say you're old, you just been. Okay, so in 1981, and then you see another one around 84, and then we jump up to the next group there. This group is actually what I would call the Fox group. These are people that joined in, including myself, although I'm not on there, during the Fox program. So we have several of those engineers that are still around. There were many more involved, but they have moved on to something else when they were done. They're fun. And the final group is the largest influx of a lot of new volunteers that I've seen in a long time. A lot of that credit goes to Frank and Jonathan for being in positions to reach out and look for volunteers. So we have quite a few younger, as far as having been with AMSAT, younger engineers, but all of them in whatever the age is, we have a lot of people, a lot of engineers that volunteer that are very smart at what they do. They're very dedicated into this segment of the amateur radio hobby in building various systems and stuff that go to space. In a look at what the value is that they provide to us, I thought, well, I'll do a little math based on a 40-hour work week, a nominal 40-hour work week. Most of our engineers, when we first sign them up, we ask if they can do 4 to 5 hours a week. And so you've got your family life, you've got all sorts of things, your day job, et cetera, that get in the way of the fun. And so running with a 5 hours per week for every engineer, I took 35 as the round number for the engineering team. So if we look at it against, say, if we were in the industry, as Robert mentioned at the meeting earlier today, so we've got 30 members working, and that would be 5 hours a week, and that would be give you about, or excuse me, 35, I should have updated that, about 180 hours. 150 hours, I can't read. Sorry about that. So 150 hours, and I round up to 160 to say, okay, that's easily divisible by 40. So we have essentially about 4 full-time employees working on all of the AMSAT engineering projects. And there are quite a few. I throw in a couple more full-time workers because there are some of us that I don't count myself, but there are some of our engineers who are invested into it and retired, and they spend a lot more time at it. So compared to a corporation, that's a really small number of people to be working on a satellite project, much less to be working, I mean just a single satellite, much less to be working all the projects that we have, because we have a ton of projects. And the big look at it in the corporate view is if you take that 240 hours a week and you take an average salary of about $74,000 that I picked up off the internet, you come out with about $450,000 worth of labor. However, I think that our engineers are probably worth a lot more than that low starting rate. So, you know, we're contributing $500,000 to even $1 million perhaps of value to AMSAT through the work. Sorry. When looking at what goes on with these projects, I know that we say, hey, we're going to do a satellite. We're going to do Golf T. That was in 2017. Here we are 6 years later, and probably a few people wondering, why is this taking so long? What's going on? Well, I admit a lot of it is unseen. It is, one of the hindrances to making it public is that we all work from our own home. So we're all working alone. And to get even a picture of what you're doing, a photo, is you know, you got to con somebody into taking it or be really good with selfies and such like that. So there's not news that comes out that way. But the satellite that we're working with the golf and the golf program, it really raises the bar in what we're looking at for going to higher orbits. We have to have a lot more robust systems and thermal power and radiation protection if we're going to go above LEO. So in addition to that, we've got a roughly 1 foot tall, 4-inch square cube that we're putting all of these systems into. And we're adding more larger systems to what we do compared to the Foxes. We have, for example, the ADCS. Attitude Determination Control System is going to be key to our ability to maneuver, point the antennas, as we were talking about, or point solar panels for power and such. And the catch with that is that with all of our AMSAT satellites, you could build that satellite if you didn't want to put a whole bunch of radios in it. And that's what we do. So the space becomes a trade when you look at it, especially if we're going to add propulsion or something like that. We've got a bigger EPS, or electric power supply and such, and that squeezes down on what we can do with the radios. So even though it's 3 times the size of Fox, it becomes a trade on what we can put into it. One of the other instances for consideration is that failure is not an option. So we've learned that with the Fox satellites. There are a few of them that are not working nominally, but once they basically leave my home and I take them for integration, then there's nothing we could do to fix them. We did a lot of work through commands and software, changing some parameters on AO109, for example, and we're able to coax some more behavior, or good behavior out of that, productivity. But really, it's very limited. Even knowing why something doesn't work is an educated guess, but still just a guess. We also have, as the #1 risk that is listed in the CSLI, the CubeSat Launch Initiative proposal that we submit in order to get the Alana launch grant from NASA, the highest risk is that we have no redundancy, basically. And so our volunteers, the people that are interested to volunteer, may be a single person working 1 or more systems. And the loss of any single person, whatever the reason is, the loss of that input, 4 or 5 hours a week or 45 hours a week, is just a major hit on what we do, and that slows productivity as well. We've also been dealing a lot, especially since the COVID era, with supply chain issues, just like everybody else. And we were looking at extremely long lead times on components that are basically kind of run-of-the-mill, although we look for automotive-grade stuff in a lot of cases. But I recall at one point in time, it was 54 weeks lead time on some of the components. And so that causes a scramble to look for stuff, alternate sources, or a delay to order and wait till something happens with that. And in doing that, we will often buy lots of that component in order to have them for a couple, 2 or 3 or 4 models of the Golf T for people to be working on. Engineering model, flight spare, and the same thing with Golf 1. So maybe call it 10 different satellite uses. So we order those in lots in order to protect against future difficulty in acquiring them. There's also the fact that a lot of things go unobtainium or the end of life that leaves us either having to redesign or having to abandon. The Fox 1s really, one of the biggest reasons that they were not continued is because there were so many parts in it that were no longer available. We'd have to redesign half of the satellite, and that was not worth the effort for that. Whereas we are moving into Golf 1, or Golf T and Golf 1, which can do the same thing with the newer construction. So let's see what else. Oh yeah, there's always also, you ever go to the store and get any potato chips and Coke lately? Costs about $100, right? And so does everything else that puts in the satellite there. So the costs are going way up. And that does take some planning to make sure, and that goes back to, a little bit to the buying quantity. We're not at PDR yet, preliminary design review. So when we're looking at those things, we're looking at them with the idea that we're pretty sure we're going to use it. So we go ahead and buy a bunch. Or if we're not pretty sure, then maybe we wait a little bit and evaluate it some more and do a little more prototyping or something. And we do have, though, and have had lately, some very good donations that have built up the bank account, if you will, AMSAT. And so that gives actually a lot of relief to our ability to overcome buying in lots, buying a bunch of stuff, and also buying newer equipment like the attitude control system, which is a leap. I think I could probably say that full system, engineering model, flight model, just for Golf T, will cost more than the Foxes, all of the Foxes put together. There we go. So we have, under the engineering umbrella, 3 programs that are running. I'm sorry about that popping. Can you hear me okay here? Okay. I have a tendency to just want to be right in front of that podium, hides my belly, you know. So we have Golf. Golf is the, and Zach talked about that a little bit, greater orbit, larger footprint. Golf, we have Ascent and Fox Plus. Fox Plus is fairly new, that was introduced to us by our newest, well, relatively new Assistant Vice President of Engineering. The Golf program, greater orbit, larger footprint, the idea of it is, in 2017, I put it to the board of directors. We had opportunities in the form of attitude determination control system partnership with Ragnarok, whom we previously worked with on the, what you might have heard is the CQC, the CubeQuest Challenge, a lunar orbiting satellite, Derby, that NASA had sponsored. And the goal of that was to see who could return the most data from the moon, or even beyond. You could go just beyond the moon out into forever. The Ragnarok, the corporation, Luigi Ballerini pulled together a team of various systems operators, if you will, to build this satellite. And it came to us that the communications and ranging was something that was in need, and that we certainly are good at, is the communications and ranging. So that started the whole process with that. In the end, that satellite was not selected for the SLS launch, which meant that they could still go, but it would cost something like $1 million. And so that was the end of that project. In that, Ragnarok, still wanting to continue development of their piece of it, the attitude determination control system, came to me, and we partnered on the idea that we would be able to give them some flight heritage and get at a low cost attitude control system for our new Golf satellites. Golf had been discussed for years before it was introduced as we put together the Fox satellites. There were a lot of opportunities that we would be together, maybe at Symposium, maybe, I remember most at a taco shop as we were doing environmental testing on one of the Foxes. And we would sit around and hash out ideas. It's your napkin exercise, I guess you'd say. And the idea of Golf is that we will develop our systems, build if we can, and acquire if we need to, systems that are going to be needed when you go to HEO. Golf is not intended to go to HEO. Golf is intended to teach us how, so that we have the expertise and the availability and the capability to do attitude changes, to do propulsion, to either work on our orbits, raise them, lower them, and also for collision avoidance. They have to have maneuverability. That's part of the orbital debris rules. So there are a lot of parts that go into that, and they require precision in what you're doing. Because if you're going to make a satellite move, you have to be very sure of your pointing and very sure of how much gas you give it, if you will. So that's something that we really need to study before we put something, up there and go, okay, let's push the button and it'll go to HEO or something. Also, along with that, the need to develop more power, systems that get more power, and that's the solar wing development. And overall, the plan is for several Golfs to be built, and this was before ODAR was clamped down. So the idea was we would be able to step up, start with a LEO, go to a higher LEO. Golf 1 was originally intended for 1,200 kilometers to be up there around FO29 and AO7, and then maybe some MEO, and getting that harsher environment, getting the capability to maneuver and steer and point the spacecraft, and the essentials we needed to not only have, but to know how to work all of these systems. So that got nixed, though, for the time being, by the orbital debris. We still plan on progressing with that. Golf T, going to LEO, we really need to just do that because anything that follows needs to be from what we find out with Golf T. Golf 1, I'm still looking for opportunities to higher orbits, and then we'll go beyond that. This is kind of just this is the view that we submitted to NASA for the orbital debris for the original launch that we were going to have with Golf T. And so it represents the Ragnarok ADCS, but the systems inside and the solar panel array that's put together and such gives you an idea of everything that goes on in there. I hope you can see it okay. What we basically have, got a laser, is this is the stack that we used. Sorry, I can't see it that well. Yeah, this is the 8mm spacing stack that we used in the Foxes. That contains a lot of the components, the systems that we're flying, that are similar to or the same as in some cases. And you go up in between it, you've got some switching with the RF matrix that Zach talked about. You've got the CIU, the central interface unit, or common interface, I forget. That's the junction of all of the signals in the satellite to the sections of the satellite, which would be the attitude control and EPS, or our typical Fox avionics, if you will. And the solar panels, that's the input from the solar panels go to the CIU to be fed through that. Yeah, that's good for that. Any questions on that? Sir.
Jerry, I did have one question from YouTube. It was going back to purchasing components. You had mentioned that you were purchasing components in a bunch. Could you quantify that any more, particularly for our questioner? Thanks.
I was gonna say big lots, but I don't know how many people are from Texas or how far out there. Well, as an example, in Fox, we would place orders because I was the one with the money, the credit card. I would have the engineers that would make a cart of the components that they needed. And then I would go pay for that off of DigiKey or whoever. In some cases, even just between the time that they did it and the time that I got there, they had a part substitution already, or missing parts, and then I'd flip over to Mauser to get that. And in some cases, you had to buy 10 of them at that time. So this is, you know, many years ago. Wow. 7 or 8 years ago anyway. So, you know, I wind up buying lots of 10. Since then, those multiples have grown to bigger lots. In other words, you got 10, 25, maybe 50, 100. And in some cases, we've had purchases of 100 units of whatever that particular component might be. That's what I mean when I say that we bought them in bunches. So sorry for not being clear.
Nope. Thank you, Jerry, for clarifying that.
All right. I did mention, actually got ahead of myself a little bit on the slide. This is about the idea of the golf program and what we plan to do. The perk, I guess, for this stepped method of learning and raising our orbit was that we're building a little bit different mission each time. Maybe one's got ADCS, one's got propulsion, depending, or a new type, checks and batteries, different solar panel array, stuff like that. Everything we want to tweak and understand the best we can as we go higher into orbit. But when it's done with the experimenting, for example, Golf T, then it's another ham satellite. And that would be the same as we go. Therefore, there would be these still populating satellites to hopefully progressively higher orbits that are available to the, you know, satellite users everywhere. There's 2 projects then under the golf program. Golf T, which I mentioned, and Zach touched on that a bit. These were both funded in 2017 when we had the opportunity for the ADCS, which kind of gave it a little push compared to what we were planning of when we would start it. But with that available, I went to the board to seek funding for Golf T, and then actually went back for Golf 1 after some discussions. And when I learned about opportunities for some possibly higher orbits. So we took that there, that was the kickoff of the golf program. And again, it was something that we had talked about, that is, we being some engineers and myself, so that we all had a plan of what we were going to do. The ADCS just gave it that impetus to go, let's just do it now, because we can get this now, we can test that now, and it was going to be the next step anyway. Both were approved. I submitted the CSLIs in November, and they were selected. Now, so selected, in other words, they agreed that your proposal was sound and that it met their goals for what they're looking for in spending their grants that they have. It's essentially a grant. They pay for up to $300,000 of launch costs, which covers pretty much everything up to a 3U to LEO. So that's the free launch part of it, if you will. And that means that when you're selected, doesn't mean you're guaranteed. It means they'll look and they will find something for you. Typically, they have always come up with something. So it's a good ride. Like I said, it's hitchhiking. You're going with whoever it is, with whatever their delays are and changes in orbit, et cetera, but you get a satellite up there for a budget price. The T is the technology exploration environment, and I pointed out some of the specific systems we want to look at with that. That's the solar panel, deployable solar panels, and this is an in-house design. They are not steerable. They simply flop open, if you will. And that raises greatly. Let's see, you would have 28 cells if you just have the static cells around the 4 sides of the satellite. The top and the bottom, because of the antenna, and in this case, I think we're going to go with a magnetometer, but those are taken up. So you would have 28 cells. If you add the wings, you've got 42 cells. So it's a significant increase in the amount of power that we can have available. I got a bigger picture of, geez, it looks so small on my laptop when I was doing it, right? I was going to say I got a bigger picture of some of these, but I'll talk about those shortly. So in the solar panel, deployable solar panel department, we also obviously needed a new space frame for 3U. And it came to pass that we filed a request for a grant, I guess you'd say, with the ARDC to fund this. And they did accept that. So the ARDC is underwriting the creation of the 3U space frame and the deployable solar panels that work with it, if you will. The 3U space frame should be good on its own. And that has been because ARDC's, preferences, and ours actually, it's open source. So it's being worked on as an AMSAT project where we can do it, removed from a particular mission at that particular time, although that's the closest when we get to a particular mission. But it's all done open source, and open source then is something, like I said, we've been looking for a long time. We have the opportunities now to start doing that, and this was kind of the catalyst for that. Beyond the solar panel that is being developed specifically for Golf T, the idea is that that could, if it's successful, also be expanded to project to have more deployable sides to it, if you will, or maybe another row of panel or cells on the end of each panel to increase the power opportunities. In the ASCENT program, which I've mentioned and Zach might have touched on, one of the things that came out of the program was the radiation tolerant IHU. That's something you were involved with, Zach, that is. The idea of it, we had a lot of experience watching the STM32L151, I think, processor flying in the Fox, and we had predictions about what radiation might do to it through upsets and such. The design of Fox was simply that if it got an upset and it rebooted, then pick up where you left off. So there were no really critical systems tied to it. And we did find that we would have resets primarily over the South Atlantic anomaly, although they can occur anywhere. The radiation tolerant IHU uses two separate chips and two separate processors, and they work together. One is the primary and the other one's the standby, basically. If an event happens to one or the other, or for whatever reason it locks up, then the other one takes over right away. And therefore, we're looking at the idea that if you have a single event upset, for example, caused by a proton, it's going to hit one of those, but not both of them. And that is the expected increase in the tolerance for higher radiation, at least at LEO, and maybe up to 1200 where we're going to fly Golf 1. And beyond that, we'll experiment some more. The IHU that was on the Fox 1 satellites, which we'll refer to now as the LIHU, as in legacy, will also be flying on Golf T. That provides, first, some redundancy, and second, it will be a comparison with the RTIHU for the relative number of times that has a reset versus the RTIHU has a reset or failure. In addition, there's an experiment from Vanderbilt University, Vanderbilt ISD, a radiation experiment, as we have flown on many Foxes, where they're looking at the count of low energy proton hits and what the results are in various commercial off-the-shelf parts, such as memory and processors and such. The experiment that they fly will be similar to the ones on the Fox, and that adds a third look at the RTIHU's capability to deal with the radiation, because through that we can get an idea if the environment is, when something happens with either one, if the environment is either the same or worse or some big difference between what we had seen with the Foxes. So it adds a little, it's not in any way scientific, I should say, but it is a comparison for looking at RTIHU performance. The RTIHU also has a radio with it. It'll do VHF and UHF or crossband, and that is going to be used for the commanding and the telemetry, the direct access to RTIHU, because we plan that would be by itself on Golf 1 with success. Just little blown up pictures of it. It's a little fuzzy, but did you show anything about this?
I did not.
Okay. Well, these are the two processors, right? Anything else you want to say? Yeah.
Hi, everybody. Zach again. So the RTIHU has two processors, as Jerry mentioned. Each of them is a TMS 570. They call it the Hercules. It's an automotive-grade safety processor, which has two Cortex R4F cores in it. And all it is it's a 32-bit ARM processor. The two cores are what we call lockstep, so that there's something inside, some logic inside, that's running the same code on two processors and watching the difference between the outputs on these two processors. And if it differs between the two, it says, oh, hey, something went wrong, and signals a fault. It has what they call spatial diversity, meaning the two cores are separate on the die. One of those CPU cores is actually rotated by 90 degrees, so it's got even some additional diversity in space. And they're running one clock cycle out of phase with each other. And these things zip along. I've actually forgotten how fast they are. Burns, do you recall the speed? Yeah, it's up there. It's in close to 100 megahertz, I believe, or over. And you might think one clock cycle to 100 megahertz is pretty fast. When you're talking about a heavy Z particle hitting you, that's an eternity. So by the time the particle has gone through your silicon, you haven't even finished that last cycle that you were on. So if you do have a bit flip in logic, you get that immediate indication that there was a fault, and that signals a fault, dedicated fault hardware inside the chip. In the center of the device here, in the center of the RTIHU, is the arbitration logic. And it's real simple. It's just a couple of 7400 series devices, logic devices, that watch the outputs of the faults from each of these two chips. And at power up, it's sort of a race condition. Whoever clears their fault signal first gets the bus. And so these are the bus switches down here. And then that chip maintains control of the bus until it has a fault. As soon as that happens, this arbitration logic shuts off these muxes, turns these muxes on, and then indicates to this processor, you now have the bus. Through the magic of Burns' software, Burns Fisher over there, and a private CAN bus between these two devices, there's a state vector that's always being updated. So if this guy is in control, for instance, this one over here has all the data it needs to know what mode the satellite is in. So ideally, when this second processor comes online, the first one has failed, the user will never know that the RTIHU has failed. Burns is kind of shaking his head, but I know you've done it a little bit. There's a little bit of time, but yeah, he'll get his chance to talk about this. The idea is to maintain the maximum amount of uptime without having to reboot the satellite, put the satellite in a situation where it doesn't have an IHU anymore. On Golf T, there will be not just the RTIHU with its two processors, but also the LIHU, and they're all connected via CAN bus. So they all kind of know the state of each other. So we really have three redundant ways of controlling Golf T. As Jerry mentioned, on Golf 1, we hope to eliminate the LIHU just because it's tough to carry around extra mass, extra power. The STM, I think it was the STM32 was the original one. It has definitely served its purpose, and it was a great design. A lot of the things that are on this board, there's a lot of power regulation for one side that was taken from the LIHU design. The other side has some experimental switchers on it, and we'll see which one lasts. So if the switchers on this side die, and we have to just rely on the side that's got the linears, well, we've learned something. That's good. Jerry also mentioned that we have a AX5043 radio modem, and this takes an SPI bus. It's meant for sub 1 gigahertz devices like, the Amazon buttons, if you guys ever saw those, where you hit a button and you get something ordered. If they weren't the 2.4 gig Wi-Fi, they were the sub 1 gig chips like this, which contain a modem and an RF section and an amplifier. But then it also has an external power amplifier made by NXP. They can give us, nominally about a watt, but we're seeing about 3/4, depending on the matching, as the downlink for that UHF. It has a separate uplink path that we can use to receive commands. And because these two processors are connected and they know each other's state, the RTIHU software has a neat mode where one of these radio modem chips is listening continuously to 2 meter for commands, and the other side is being used to transmit telemetry continuously. These chips are not full duplex, so you can't listen and transmit at the same time, but by creatively using the two sides of the RTIHU, you can emulate a full duplex system. Now, to be clear, this is just for command and telemetry. This is not for user traffic. It's not a PACSAT. It's nothing else. It's just for operations, AMSAT operations use. But I believe Chris Thompson actually has had his software demodulate. And I'm kind of looking at him. You got it to demodulate the RTIHU's telemetry, correct? Yeah. Okay. So it works just like the Foxes right now. Pretty much everything I had. Thank you.
Thank you much. I'm going to do that again with the next system we get to here. The ADCS. This is the Attitude Determination and Control System. Ooh, sorry. And originally we were going to go with Ragnarok as the provider of that. Ragnarok was unable to meet the timeline necessary for the Golf T launch. We had a launch actually manifest at that time. So we had to back out of the launch opportunity and look for something else. So what we found was one of our members, Hilly Page, who is, I don't recall his call sign, but he is out at the University of Arizona, is that right? Out at the University of Arizona, and he's a graduate student there, and he has, he's graduated, and he was working on an ADCS for another CubeSat mission that they had going out there. He was able to give us a really thorough rundown of the various ADCS that were available commercially and their value, bang for buck, if you will. He also had experience with this particular brand, which is the CubeSpace ADCS. So that led us to where we have purchased, or we will purchase and use the CubeSpace ADCS for our systems. Right now, in the development of it, we have their flight computer, basically, they call it the Cube computer, just to work as an interface to make sure that we can interface with their flight computer from our IHU in order to receive and send commands and various information of that sort. It does provide 3-axis control. It does have an option for star trackers. We don't plan to use them right now, and it will be able to use of magnet torquers as well as reaction wheels for our purposes. So that's a device under test with this as well. Have they flown before? Anybody remember? I think I'm pretty sure they have, or at least they've sold a lot of them. So, but it will be for us that learning curve. Not only do we, engineering, have to figure out how to talk to the ADCS and understand what it's saying and make that into a meaningful communication, but we have to design the capability for our operations, which is Drew Glassbrenner and Mark Hammond, to be able to send commands to the satellite and point it in a particular attitude, and then also receive the data that verifies that or gives them an idea of what they might need to do to point it. So it's not just a engineering problem, if you will, to get the ADCS integrated, but we also have to be able to provide a user-friendly interface to ops to be able to operate it. Got some blowed up pictures of this too. The one on the left is actually a 3D printed representation, a model of this portion of the satellite. And Tom Karnauskas did this. He's working on getting the stack inside of the frame. And that was his challenge with this one. You'll see we do have offset rods because of the size of the ADCS versus the size of the rods and the circuit boards we had on our typical bus. Here's your EPS right there. And then you've got MPPT and the CIU sandwiched in there. And, whoops, sorry. Well, I hope you enjoyed that. Let me see. Come on. There we go. And the computer board, for cube computer for the module. And then over on the right is their flyer image of an entire unit with all the whistles and bells. And so ours will be similar to that. We have the SDR and 10 gigahertz data downlink. The 10 gigahertz data downlink is working for high-speed data downlink. This is something that has come up through some of the industry shows we go to, where prospective parties, interested parties in partnering, typically universities, we will, of course, fly experiments for them. We carry that for STEM experiments. And it turns out that our data speed in the Fox satellites that was perfectly satisfactory for Vanderbilt, as well as the Virginia Tech imager camera and the University of Iowa Herky experiment, which unfortunately didn't work to its fullest extent, so you haven't heard much about it. But they were talking about high speed. Therefore, in looking at our move to microwave and the ability to provide some data at a higher speed downlink, that's what this experiment's about. It uses an Edis E10 SDR, and its primary mission is solely to bring that, probably our telemetry, unless we preload some other stuff in it to keep it busy, but to do that downlink there for the test, at least to satisfy the CSLI. Beyond that, because it became something that was early on rather easy to achieve, kind of like the L-band downshifter that Zach talked about, where we could put a board in that Fox satellite and have an L-band uplink without really changing much. The ability to have the 10 gigahertz through the SDR repeat the downlink that's coming from the transponder, the VHF up, UHF down. So the SDR just picks that off, and then it will also transmit it down on 10 gigahertz, which is something that we're going to find useful for. My plan is that as we transition to more microwave things on the satellites, as we go higher, which is where they really become important, having something like this now gives people an opportunity to experiment. And the voice part of it gives you the opportunity to operate the transponder like you would basically on the uplink, but listen for it on the downlink on 10 gigahertz. A closer view of some of the items Zach had shown earlier. This is the PA, and that's the radio. Now see the way the radio sits, I'm sorry. It is a size that isn't anywhere near what we would like to fit into the stack of the satellite, but we cannot alter that. We had asked them actually if we could take the PCB and kind of rework it so it would be a little bit smaller, but they did not allow that. So the way it works out is that this particular satellite's got this really goofy stack arrangement where we have, like I said, this is some of the legacy stuff in a sense right there. And this is the new stuff, which includes the SDR power, et cetera, or ADCS and power and such. And then the SDR is just kind of stuck up against the wall here. And that was a little bit of a, well, that's one of the things that makes things go slower, right? When you're working on that and you've got to go, okay, how are we going to fit this in that 12-inch cube there? But that worked out. Hopefully we will be beyond that. And you can hear a little bit more about that shortly, but there's a project in Ascent that we call SDRB, where the work is being done to redesign the basic function of the E10 down into a 4-inch square, roughly PCB, which is what we use on our stack. Golf 1 then. Golf 1 is not a lot to say about it right now. It's going to be dependent upon, but hopefully the same mechanical design as Golf T. It will also carry the same ADCS, assuming we have no problem with that, and planning on expanding perhaps the power, the battery cells from a 4P2S, wasn't that it? 4S2P. Well, add another bank of batteries for more power. Does it do it again?
4 serial 2 parallel.
4S2P. Okay, 4 serial 2 parallel, and make it a 4 serial 3 parallel in order to give us a little extra boost. Because with Golf T, we know we're right up against the power margin for everything that we have in there that we want to run. So that's going to be another thing that we'll learn from it, is the balancing of that in order to get the best performance. Adding a little bit more capacity will be good. That becomes a volume and mass issue though too. The final design then of Golf 1 is based on Golf T. We are learning things as we design Golf T and go into preliminary prototyping and flat sat and eventually engineering model, for example, of what works or doesn't work. So we have that knowledge already going into Golf 1. We will learn more, especially when we're done with the flight model of Golf T, and hopefully get some experience with Golf T on orbit before we have to close Golf 1. So the schedules for those right now are that Golf T, we plan, the target is to deliver it in the second quarter of 2025. And typically that means that they've got the launches down to where it's about 45 days from delivery to launch. So that'll put launch somewhere around the middle of 2025. And then ask take about 18 months from our completion of Golf T. And this depends on how many people we have and such that we might work ahead, but before we launch Golf 1, before it's ready, December, I think I made it November. November of, could have been October too, fourth quarter of 2026. And so that gives hopefully enough lag that we do get a little, like I said, on orbit telemetry and observations and lessons from Golf T that we can work into it. We did not have that opportunity with the Fox satellites. They were so popular, and we had Vanderbilt University even submit 2 of the CSLI for them, that those just wound up being kind of cranked out like toasters or something. And so what we found out wrong with Fox 1A, we made a little tweak. We were able to make some software tweaks with them, but nothing substantial like was envisioned originally. In Golf 1, we go back to our educational platform, if you will, where we have ham radios with some experimental stuff in that league, and then we carry STEM experiments. STEM experiments is one of the greatest outreaches I have seen to education, involving students in creating experiments for whatever the case may be. In this case, for Golf 1, we're looking at high school in San Diego has the desire and has been working on a camera experiment, so we can, or they can take images, if you will. And you can't beat that, in my opinion. You've got the students, they work on this experiment. It's something that needs to fly in space, and we're an easy ride in a sense, right? So they don't have to try to build a satellite around it, because that's a tough part of trying to do that. So also Vanderbilt, again, Vanderbilt ISD, as I said, are close partners and regulars. They're testing COTS things, testing radiation testing things that we're, that we will use or fall under our projects and such.
Stack looks pretty full. Where are these going to fit?
I'm sorry, what?
I said our stack looks pretty full. Where are these going to fit?
Oh, those?
Yeah.
Well, if we, for one thing, it's shrinking down the what do you call it, SDR. You take it, and getting the stack back in the order of being a stack. The Vanderbilt experiment is two boards, and there is quite hopefully, a gap between the 2 stacks that are there. And the camera is very small. It can probably be mounted to the wall, in a sense, like the SDR is. with no problem. That's the current view. It can look out the -Z, the end with the 10 gig microwave antenna on it, the patch antenna array, because it just needs a little hole between those, and that's a possibility as well.
Okay.
And yeah. Just in general then saying that is that if when we can get an SDR to be stackable, then we can go back kind of the old game of just putting everything in vertically, essentially. One moment, please. I don't know how many of you from Texas or have ragweed allergies, but antihistamines dry you out really well. Thank you. Sorry about that. And then we've got, of course, the microwave. And Zach talked about this. We have, with what's on Golf Tee, the ability for the 10 gigahertz downlink. We have ability for, pardon me, well, I don't call it necessarily an uplink, but we do have that 432 or 70 centimeter, which kind of initially started as a pickoff in order to get that transponder signal to be able to repeat down on 10. We have in that multiband antenna 1.2, 2.4, 5 gigahertz. The long range target for AMSAT was what we called 5 and dime. That had two good starts with the CQC, the CubeQuest Challenge lunar orbiting satellite. That is actually where that originated, as the engineers there looked at the volume that was available and what frequencies would work best for the communication with that satellite, essentially. And it was based in part on the fact that both 10 gigahertz and 5 gigahertz have typically surplus or consumer components available for work on ground stations and such like that. And then over in Europe, as you know, they have QO100. QO100 uses 2.4 up and 10 gigahertz down. So we have the opportunity of, in Golf 1, operating 5 or 2.4, or maybe both, as uplinks, so that if Europe, when they want to use it, it would be no change. And essentially, they wouldn't have to have a 5 gigahertz piece as well. Pardon me. And so that gives a lot of opportunities. The 1.2 gigahertz is not worldwide. And actually, I've had some fun with the ITU when we put up the L-band satellites, because countries would, you have an opportunity to call for a coordination, I guess, with particular countries, and they would send stuff to the FCC, and then that would come to me, and they're saying, well, your 10 gigahertz there is going to mess with our, 1.2 L-band is going to mess with our local GPS satellites or what have you. Fortunately, I was able to say only, tell your hams not to use it then, and it won't be a problem because it's not a downlink. So as an uplink, and especially over the U.S., I think it might make a good command channel. That where we're going then too, with the 10 gigahertz, is that you've got a lot more bandwidth to work with, right? So, not like 20 megahertz transponder or something, for a dumb example, but an example, then you're going to want 20 megahertz worth of stuff to uplink, possibly, and therefore if you put it on 5, you got that. Even 2.4, I'm not sure how much you will fit, but the 1.2 then is a good way to get out of the way, because the VHF, UHF capability will continue, and it will be omnidirectional as it is now, at least for Golf 1, because we need that fallback. I'd like to get a time check.
You do, Jerry. So, yeah, I think we're going to do a break here pretty soon. We've got about 9 more minutes, and we're going to do the Fox Plus after the break. So if you want to take some questions now, or I don't know when your transition is, if you would go toward that. And you're muted right now, by the way. Okay.
All right, I'll just go faster. Ascent is the skunkworks. Skunkworks was proposed by Dr. Tom Clark back in 2015 as a place for engineers to go develop things that are just in a sandbox, go play. So that is what they do now, and that is what has created some of what is flying on Golf T, Golf 1. and we have much more activity there, which is something Jonathan had on his bit of slides here. It's turned out to be a really good thing because it's free of being tied to any particular mission. So in the case of Golf 1 or Golf T, for example, Golf 1, the design of that satellite incorporated some of the stuff that was thought of in AMSAT. So that's how that's kind of intended to work. It's not targeting a particular thing necessarily. And this is where we cut it. All right. So questions?
Just kind of overview of power budget. When you have the deployable solar panels, when they're fully illuminated, how much total PV power total from all sources will you have? And number two, how many watt hours of battery? You're talking about expanding the battery. How many watt hours of storage will you have there? I'm assuming the PV panels are going to be illuminated roughly 50% of the mission.
In looking at the design, the idea for those deployable fixed panels, it was calculated at basically 3 different levels. One would be full sun, one would be about 45 degree, and one would be less than that. And the total capacity at full sun was on the order of 19 watts. Is that right?
36 or 37 watts.
Okay, I'll go with that. Full on sun. 36 or 37 watts straight on. Yes, and the calculations were that if we're going to allow for the fact that we're going to be testing ACDCS or pointing the antennas toward ground, then the average would be something about 20 watts. And that's what we're working with right now. And that's only the number I recall. If anybody, other engineers here, have a better answer, I appreciate it.
Was that average over the orbit or just when it was at a certain point? When you say the average,
Yeah, I know. I am honestly trying to remember specifically. It's something that I don't think it was
Okay.
orbit average.
okay.
I think it was average that we could generate.
And the other question is, how many watt hours of storage were you thinking about putting in there with the battery? And what technology of batteries?
They're lithium iron phosphate, right? Lipos, and the bank that we have right now, I think the cells changed from when I first recall looking at it specifically, but we're talking about somewhere around 78 or 80 watt hours. Is that true? With the increase, the increase to third string, plus they were a little bit bigger cells. So, but originally the Golf T was specking out at 141 for that launch there. So that's what I hope to get back to, close to that. Anything else? And I apologize, I kind of got shorted on time a little bit there. I'd still like an opportunity maybe for all the engineers that are here to either answer questions or come up and do a little elevator speech. I think that's very valuable compared to what I do based on trying to remember everything they do.
Exactly. I think we have time for a few more questions, just maybe 2 more questions. I've got one in the back corner here for you, Jerry, and I've got one up front. So just a second.
So I wanted to know if you're transmitting 1 watt down, but just 1 watt transmission power down.
On the
We'll say on the ham bands,
excuse me again, the last
on the
part?
on the amateur radio bands,
Yeah, I realize
transmitting
that.
1 watt down.
It depends on what radio's working in. It's a short story.
Okay.
Golf T is flying the same transponder as AL 109, which is kind of like an average of 650 milliwatts, I think, right? And then the SDR, honestly, I don't know the straight answer to that right offhand. How much is the SDR doing? We're doing about 2 watts, I think, or something.
So if you go higher altitude,
We'll boost that.
okay,
See, the
Okay.
CQC, the lunar one, and also Phase 4B was going to use the same thing. The PA design was done for 10 gigahertz to provide 10 watts out of a module, 40 watts total in the case of Phase 4B, or 20 watts from the CQC by 2 antennas, 2 finals there.
I think you were the one that answered earlier, a wide beam width is expected. What does wide mean? Is that like 15,
That's a nice broad one, isn't it?
45?
Well, Kent stated that what it is in the X-band case is that it will cover the whole Earth. So that it's, and I don't remember what that number is, but essentially in talking about that radiation pattern as well, he said it can be more off the side. So the idea is that it doesn't have to be pointing directly below, and it gives everybody a better opportunity to be able to get it, especially since it's going to be scooting it, you know, in Doppler at that height. I'm done. Thank you, everyone.
All right. Thank you very much, Jerry.
Can I do a quickie? I'd like to ask all my team that are here to stand up, please, for just a moment.
All the engineering? Yep, there we
Yeah,
go.
all the engineerings. And here comes the bus, guys. Okay, so what I'm thinking is, because we didn't get the chance for Q&A and such like I thought, would you guys be willing, if anybody wants to come up and ask you something about your system, you know, in general, to just go ahead and talk about it? They're going to give you better, more detailed answers than I can, and so we'll work that out, but I think you'd be able to ask them for some more detailed questions.
Thank you very much, Jerry. A round of applause for Jerry, please. Jerry Buxton.